I never get that code wrong. What's going on, chat? It's your boy Leo, and we're back with Physics 2. Let's go. Let's go. Sheesh. My grade goes down every day, baby. Let's go, Leo. Yeah, at least I'm doing good on my labs. The only group assignment. Alright. Today's challenge might be difficult for some of us. Mostly me. We're gonna try to pass physics. That's the goal. We want to get this to a 70. How are we gonna do that? Well, I'll tell you, it's pretty simple. Proctored pre-lab assessments. Every 3 weeks we got a test we gotta take, and it's worth a whole lot of points. All we gotta do is get an A on one of them, and we basically pass the class. And there's one tomorrow, so that's what we're doing today. We're gonna see if we can get an A on the test tomorrow. We're cooked. We're so cooked. That's not happening. It's not happening, chat. The last one would have been 3 weeks ago, so July 1st. I haven't done a lick of work since then, so pretty cool. Magnetic fields, electromagnetic induction, inductance, alternating current. That's 4 units we gotta cover, which feels like a lot of units to cover in 3 weeks, right? 1, 2, what? You had 2 modules in 1 week? Oh my gosh. Chat. Okay. We can read, but who likes a reading stream? Wait, that kind of sounds hype, low-key. Wait a second, that's kind of cool. I don't know. I like that. Reading stream, guys? Reading stream? I don't know, guys. That sounds pretty cool. Wait, oh, it's backwards because that's the wrong scene. And then we just switch to this one. Oh, I was gonna say, what is this? What are these recommendations? That is not my account. That is a different account on this device, and I will not say who it is for privacy reasons. Well, I was at a Peppermint Parkway for the first time today, while at the gym. Oh, I've never been to the gym, guys. You can't. Future video. Okay. Anyways. Let's get it. Let's get it. Come on. All right. Let's go. Is this illegal? I don't think so. Good question, though. Let's go, baby! He's reading the textbook! I've never read a textbook. It's true. I have 2 hours. Fudge. We're so cooked. Chat. We're actually cooked. Chapter 28. This is important. Nothing substitutes for reading the text. Master examples presented in each chapter. Understand what each figure is saying. Test your understanding. Study the discussion questions. Everything. Okay. Okay. Well, the sheer amount of stuff we gotta get through to get to it is crazy. Doesn't look too bad. It looks horrible. It looks You're disgusting. If you actually think that's not that bad. Okay. Magnetic field produced by me. Where's volume? I don't see it. Okay. We are on chapter 28. Alright. Sources of a magnetic field. Yeah, that's the chapter. Yeah, chapter 28, sources of magnetic field. Okay. Oh, you're basically telling me what I know to learn. This is the same. Alright, chat, let's dig in. Is there a way to take notes? Oh, fudge. Okay, we're actually going to want to take notes today. Piece of paper. Awesome. 28. Okay. Let's start with the basics. The magnetic field of a single point charge, Q. So these point charges are called Q. And it's moving with the velocity V in a condition, such as a solenoid shown in the photo that opens this chapter. Magnetic fields are produced by tremendous numbers of charged particles moving together in a current. But once we understand how to calculate the magnetic field due to a single point charge, it's a small leap to calculate the field due to a current carrying wire. We call the location of the moving charge at a given instant the source point, and the point P where we want to find the field of the field point. Source point, field point. Find the field, where we want to find the field point. In this section, we found that a field point, a distance r from a point charge Q, the magnitude of the electric force field E, the direction of E for positive. What the hell who are you? You're scaring me. Get out. Experiments show that the magnitude of B. What's B again? What the hell is B? The magnetic field. That's what I thought. Okay. There's this magnetic field B, and it's proportional to Q and R1. But its direction is not along the line from source to field. Instead, B is a perpendicular plane connecting this line and the particle's velocity V. So if you take doink, right line here, it's gonna be this thing, Majiggy, right? The right hand rule. I haven't learned it yet. That's what we're gonna learn today. That's our first goal. B is perpendicular to the plane. Oh, right. So if you have a plane with this guy and this guy is coming out. Oh, here it is. Okay. Right-hand rule for the magnetic field due to a positive charge moving at a constant velocity. So if this positive charge is moving at a constant velocity, you point the thumb of your right hand in the direction of the velocity. Your fingers now curl. This curling thing is goofy. Curl around the charge in the direction of the magnetic field lines. If the charge is negative, the fields are in the opposite direction. That's confusing. So it's, I assume, left-hand rule. For these field points, R and V. Wait, if the charge is negative, the field lines are in the opposite direction. I assume the field lines equal the curl. No, okay, so field lines like this for positive, for negative field lines go basically counterclockwise or whatever, counter-lie-wise. For these points, R and V both lie in the plane. The beige plane? Oh, the color beige. Okay, I was going to say, that's a goofy name for a plane. Which one's the beige plane? I don't know. Now I see this. R and V are in the beige plane. Up to P. What is P? We don't know. P is R. It's the value of R, I suppose. Is given, we call the location of the moving charge at a given point. The source point, and the source P where we want to find the field is the field point. So this is a field point, which is where we want to find the force. The force of what? Where we want to find the field. What does that mean? The point P where we want to find the field point. That doesn't make any sense. For these field points, R and V lie in the beige plane, and B is perpendicular. Okay, so B comes out of P, which is the point, where this guy and this guy kind of meet up. View from below the charge. Why would I want that? What the hell? So B's rotating this way? You mean behind the charge? Okay, yeah, behind the charge. Magnetic field vectors due to a moving positive point charge Q at each point B is perpendicular. Yeah. Moving charge, vector magnetic field. We can incorporate both the magnetic and the magnitude and direction of B to a single vector equation by using a vector product. To avoid having to say the direction from the source Q to the field point P over and over, we introduce a unit vector called R hat. R hat is from Q to P. So, in other words, this guy. Oh, this is the unit vector. So the direction of the R. And the R is from this guy to that guy. Okay. Yeah. So, like, in other words, the dot product of R and P equals that or something. We used R for the same purpose in some other unit. I don't remember. This is my first section I've learned about. Given the magnitude R over R, then magnetic field due to this, take R hat, the unit vector from point R charge, distance from the point charge to where it's measured. Let's write that down. So we got B, which is the mag field at P with constant velocity. So mu 0 over 4 pi. This is the magnetic constant, and hopefully we'll learn about what that means in a second, times this charge Q. So I assume that just means the charge of Q, times this velocity vector V, which I assume is the velocity of the charge. But we're going to take the cross product of that with R hats. Which will give you the perpendicular. Yes, sir, we're cooking. And then R squared, because the first R represents the magnitude of R to the point P, and Q is the charge of the guy, times the velocity. When you multiply the charge by the velocity, you get the magnitude of change. Holy moly. I'm too good at this, chat. I'm too good at this. My goodness. Unit vector to P. And then this guy is distance to P. And what's the point that we measure it from? It's just Q, right? But is there another name for Q? Doesn't seem like it. That's weird. Yes, there is. There definitely is. You said it earlier. It's just a point charge Q. Yeah. Okay. And that's the source point. We don't know the name for the source point, though. There's no, like, letter for it. A point charge in motion also produces this thing called an electric field, with field lines that radiate outward from the positive charge. The magnetic field lines are completely different. For a point charge moving with velocity v, the magnetic field lines are circles. We know this, centered on the line and lying in planes perpendicular. It's like kind of like a box, and it's going like whoop. With the curl, you know what I'm talking about. We'll encounter in this chapter. Grasp the velocity vector v with your right hand, so that your right thumb points in the direction of v. Your thumb is then curl around this line. We've done this like 3 times now. Ba 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 ba. Okay, now unit stuff. Unit stuff. We're gonna have this be a section of the paper. 1 Tesla T equals Tesla T equals 1 NS over CM, which is equal to 1 NA over M. No, N over A times M. Wow, I wrote that completely wrong. What's a C? What is C? What's your problem? You're not giving me good stuff. What the frick is a C? How hard would it be to write it for me? Is C the measurement of a charge? No. Shut up. Whatever. We'll be fine. I'm sure we'll figure out what C is later. We are not figuring out what C is later. Using this with that guy, we can find the units of the constant. 1 NS squared over C squared equals 1 N over A squared, which is equal to 1 WB over A times M, equal to 1 Tesla meter over A. And from mu0 is going to equal pi e negative 7 t m a. I'm not gonna write the rest because I'm stupid. The value of the speed of light in a vacuum. One over the square root of that guy times this guy. But I don't know why that's important. Forces between a moving what? Coulomb's law. What is this? What did you do to me, man? Why doing this. Let's just run it. Let's just run it. On the paper? Low key, yeah. On the paper, dude. Alright. We got this little plus guy. And he's got a little... Okay, let's do the dotted lines at first. Okay, and then we got this other little plus guy here. And we got his little R prime. And we got Q1 and we got Q2, we'll call that guy. And then we got this guy here. We got a B coming out. And then we got this velocity, which we'll call V. Negative V, but I assume... Well, this is confusing. I don't know if we're talking about the same guy here. Alright, so the height is the velocity, is the R. Yeah, we know this. We know this. And then we got F, E, and we got F, B. So there's a magnetic force, obviously, because it wants to get away from the other dude. I get it. But it seems like the force due to magnetism is equal to the force, is in the same direction as the force due to electricity, which I did not know. I don't know if that's just because there are only 2 points. Maybe when you introduce a third point, we enter the 4th dimension and like stuff gets goofy. But I think that's it. Okay. Coulomb's law gives the electric force Fe. We'll write this next to it. So, Coulomb's law gives Fe on the upper proton. The magnetic force law gives Fb. The magnetic field that the lower proton produces at the position of the upper proton. The field vector from the lowest proton, the source, to the position is R. We know that though. Execute from Coulomb's law the magnitude of the electric force. So Fe would be equal to 1 over 4 pi, little weirdo, times Q squared over R squared. Actually, we'll call it Q1, Q2. Q1, Q2 over R squared. The velocity of this... The velocity of the upper proton is negative v. Is it really? You should have told me this. Okay. Fb equals Q2 V2. Not V squared, V2, buddy. Bro. Wish I had an eraser. V2. Cross product B. Which is equal to mu 0 over 4 pi times Q1, Q2, V1, V2, R squared times, I'm not even going to call it R hat, because that's, I mean J hat, I'm going to call it R hat, because I'm a real man. Alright, we're trying to make this conclusive. There's no I, J, and K. Those are made up values. I'm going to use the real ones because we're going to derive the actual formula. I don't have time for your little baby, goofy little... Huh? Magnetic interaction in this situation is also repulsive. Ew, you're repulsive. Sorry. The ratio of the force magnitudes is FB. What the frick? And then FB over FE equals mu 0. Q1, Q2, V1, V2. Well, it's low-key, it's like the magnitude of V1, V2 though, because we're squaring it. What is this horrible music? But it's not really the magnitude of V1 times V2. Why is V multiplied by V? Does anyone have a good reason for that? Is the velocity of the 2 points always going to be equal in magnitude? This we will never know. Alright, whatever though. 4 pi r squared, and then do this over q1, q2 over 4 pi, this little girl, 0 r squared, which equals E0 mu 0 v squared, basically. And then v squared over c squared, which is interesting. So it's the velocity over the speed of light. That's cool. Wait, that should be like a really small number then, or something. Fe is bigger than Fb, so that makes sense. Right hand rule for the magnetic field due to a current element. Point the thumb of your right hand in the direction of the current. Your fingers now curl around the current element in the direction of the magnetic field lines. For these field points, R and DL both lie in the beige plane. Okay, gotcha. DL is where? Okay, yeah, I. So maybe you're talking about DI? I don't even know anymore. Or L? Whatever current is. So you got current I. Then you have DI, we'll call it, because I don't know. I can't read. DI is, I assume, the differential quantity of inductance or current. Because who makes these letters? It's horrible. Inductance we haven't gotten to yet. Alright, just chill for a moment. dB would be the thingamajiggy going this way, and it's capital for some reason. And then, yeah. So I don't get dB though. What's dB? Where did you have this somewhere? For electric fields, there's a principle of superposition of a magnetic field. The principle of superposition of a magnetic field is the total magnitude caused by several moving charges and a vector sum of the fields caused by those individual charges. So we're combining crap now. Yeah, we're having multiple moving charges, and I assume they're moving in different directions at different speeds, and we want to figure out the magnetic field vector at a certain point, would be my assumption. And what you're saying is you can't do that. There's no way of finding it because it's a superposition. That's getting into quantum physics, isn't it? We begin by calculating the magnetic field caused by a short segment dl of a current carrying a conductor. Oh, yeah. The volume of this segment is A. Okay. Where A is the cross-sectional area of the wire. If there are n moving charged particles per each unit volume, each of charge q, the total moving charge dq in the segment is this. Okay, let's draw this out. So we're going to have this little die. And he's going to be like this. I. Moving charge dq is equal to nq a here dl. Whoa, that's not a good L. Whatever. I guess that's how we're gonna write them from now on, though. I'm gonna call them DL because I'm cool like that. Oh, brother. Oh crap, is right. So first we're gonna draw out this guy. So DL is in the yellow plane, is what you're claiming. Right. Okay. I like you. You're fun. You're fun to play with, my friend. So at this point, for example, you would have DB here. Or, alternatively, wait, is R hat? R hat's not this guy. Cancel that. Yes, it is. It's not this guy. Fudge. What is that then? Nothing. There's nothing there. You have this little guy, R hat. No, that's not R hat. That's R Majiggy. This would be R hat. And then the R hat goes here. And then we got another guy, which is DL. Oh wait, what is DL then? Fucking no, man. I can't keep track of this anymore. This is the DB equals 0 plane. Line. Both lie in this beige plane. So I'm dumb? What does this DL represent? That's just the guy going this way at this point. Fudge. What is the yellow plane then? Alright, well that's useless for me then. What is DB? DB is the guy that's coming out of the Majiggy. DB is this line. Yeah, we got it. We got it. Don't you worry, baby. We got it. So we got DB is equal to mu 0 4 pi times dq, we'll call them. We'll put this times v of d sine of angle r squared. Which is equal to mu 0 4 pi idl sine guy over r squared. Vector magnetic field. Yeah, the vector length of the element. The unit vector, the magnetic constant, magnetic field due to an infinitesimal current element. Uh-oh. Rho which means, in theory, B would be equal to mu 0 4 pi times the integral of I dl times r majiggy r squared. Current element, magnetic field lines. Show the vector. The field lines dB and the magnetic field lines of a current element are exactly what? I don't know. I lost track. Like those set up by a positive charge dq moving in the direction of the drift velocity. So we're talking about this thing called drift velocity now. I did not pay attention. What is the drift velocity? Is the frick? Where did drift velocity come from? Okay. The field lines are circles in planes perpendicular to DL and centered on the line of DL. We can still verify these equations indirectly by calculating B for various current configurations. Okay. This is fun. I'm getting it slowly. The relevant concepts. The law of Biot and Savart allows you to calculate the magnetic field. What is this law? Is that this guy? Equations 28.5 and 28.6 are the laws of Biot and Savart. Cool. Okay. As you calculate the magnetic field at a point P due to the current carrying a wire of any shape, which is cool, I guess. The problem using this steps, this guy here, that guy there. Yeah. Bah, it's probably easy. We're gonna do a practice problem. Give me at least something a little difficult. Oh my god, we're still in 28. Fuck, we're so cooked, guys. We're so cooked. We're not making it out of this one. Dude, we don't have time for this. To find a magnetic field produced by a straight current carrying conductor. This result is useful because straight conducting wires are found in essentially all electric and First use this guy. Fuck. Shit. We're so much trouble, guys. Okay, let's just draw this out. I'm sure it'll be fine. Let's see how small we can draw, I guess. Okay. What is dB? Is the blue thing dB? that's point A to negative. Okay. So with these points to A, x squared plus A, because A is in the y direction, then A is much larger than x. Considered to be infinitely, well, yeah, obviously. That's the condition if A is an infinitely long wire. When would this even be useful? So if we assume A goes on forever, then the B created would be this thing. Okay, sure. Why not? Which is basically R. So that's cool. And if I have a wire. And we have all of these magnetic fields. With this line called I. The geometry in this case is similar to an example. Okay, I don't care. Put the lines of B, the magnetic, have a completely different shape than the lines of the other thing, proportional to 1 over R. What's proportional to 1 over R? The magnetic fields in both problems are proportional to 1 over R. That's correct, yes. A long straight conductor carries a 1 amp current. At what distance from the axis of the conductor does the resulting magnetic field have magnitude? B is equal to this. So we want to find, we have B, we want to find X, basically. I like that. That's fun. Then we also know that R is equal to mu 0I over 2 pi B. Values. Mu 0. I just want to write down. I think mu 0 is pretty consistent. What is mu 0, by the way? Is this mu 0? I don't know. I can't say for certain. Holy shit. This looks horrible. Every other question looks like a nightmare. So yes, it equals 4 pi e negative 7 Tm over A. 4 pi e negative 7. That is never being remembered. Okay. So you take that, then you got this guy, the number of amps, so the amplitude, the current, and then we divide it by 2 pi, 0.5 times 10 to this thing, which is B, which we know, because it's up here. What's up, Mom? What do you think I'm doing?
I don't know.
Studying.
But I hear you talking to someone.
Yeah, I'm recording.
Did I to you to ask you? So obviously, how are you studying if you
I got a message. What's up?
We need to leave at 5.
5 now? I guess that makes sense because it's a 40-minute drive. So you want me to leave soon?
At 5.
Okay, I'm gonna go a little faster then. So we get 4 millimeters. Alright, now for this goofy little nightmare of a problem. So if we have this thing, we have 2 wires. They're these distances away from each other. Wire 1, wire 2, wire 1, B1 here, there, B2, the total of each of these would be the added vectors of the quantities. So if we have these 2 wires, then in the middle would be the highest B total. X and Y. Are you serious about this being 28, 29, 30, 31? That's freaking insane. We're not making it, guys. D3D over here. Why do we know this? Why do we know this? I need to know why we know this. That's very important for me. I need to know why we know this. Fuck it. We'll be fine, I'm sure. Holy shit. Which is, oh, I prime is the current in the second vector. So much trouble. Why is there so much stuff to write? Okay, the circular in the segment dB with the differential components perpendicular to the dBs combined to give the total B field of the P. So P dB, dBy, dBx, dB of all of the points that dB would end up being going. What the fuck is dB doing? Oh yeah, from any point. It's gonna look like that? That's insane. Because, yeah, it would be like a perpendicular looking goofy ah. So, basically, you have all of these guys, and they're going down, and then we kind of create a right angle here. So, the angle here is equal to the angle there. And that's the dB at every point, which I assume means if I added all of them up, I would get 0 as the total dB. But this is not true because dB is going in this direction. But if I combined all the dBys, I would get 0, theoretically, while dBx's would all be added up. And I assume the answer for dBx from a circle is going to be... Why is it that complicated? Okay. So if I have a circle of I have this guy called Bx coming out, which is going to be equal to mu 0 IA squared over 2x squared plus a squared 3 over 2. Yeah, right hand rule. Okay. Thank you for the right hand rule. So the right hand rule works both ways. If it's a loop with I, that's my right hand. Yeah, and the curls like this with the loop, then B's coming out. Let's go, baby. Let's go. So, what the hell? Okay, so this looks like an easier formula to remember. Ni 2a radius. But then there's this other dude called n, which is the number of loops, which I assume is for like coils, which is pretty obvious when you think about it. Yeah. Oh my gosh, if we're only taking part of a coil. Oh wait, I saw this. I've seen this question before when I was doing the homeworks. This is an important question, I believe. Magnetic moment. Substituting the result into this equation. I'm sure everything will be fine, guys. Bx is equal to this. Yeah. Yeah, we'll be fine. Sorry, let me go back, because I wrote something goofy in my equation, and I'm not sure if it's right. There's a 0 in there. Why did I add a 0? Yeah, there's only one 0. IA squared. Distance along axis from the center of the loop to a field point. So yeah, that is x, which makes sense. And A is the radius of the loop, which is, that checks out. Alright, chat, we're good. Ampere's law. Ampere's law says that B, the integration along a path of BDI, is equal to this dude. Sure, I'll write that. That's a pretty easy thing to remember. So, well, I guess we'll just write this. This probably didn't teach me this earlier, though. Yeah, so... But why is this important? There's why it's important. Holy moly, if it's a goofy looking shape like this, things get nasty. Around the integration path. Okay. So weird. So weird. I just want to move on to the next section. God damn it. Okay. Just keep paying attention, Leo. Don't give up. 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 Come on. Also move a little faster. So we got the B's going around like this. We got the R going here. If R is greater than R and R is less than R. Okay. Why is this important? Outside of this conductive area. So you're saying this is the conductive area? I guess there would be a magnetic field within the magnet itself. I've never really considered that. Is that what we're talking about here? The cylindrical conductor with a radius r carries a current here. The current is uniformly distributed over the cross-sectional area of the conductor. Find the magnetic field as a function of the distance r from the conductor axis for both inside and outside of the conductor. That's cool. Yeah, so it's a sloped value as you leave, and then it goes down like so after hitting r. My question is, what is the curve for? The curve before is this. Because it's r over r squared. This is a circuit. Oh my god. Of course there's... Of course it's applicable to a circuit. What else would it be useful for? Stop it! Stop it! You're kidding me, man. The Bohr magnesium. Why? You're making up stuff now. Just because you think it's fun, don't you? We have inductance. And we have V. And we have U. Oh, stop. Stop. Okay, V travels in almost a direction as current, I guess. Fuck. Paramagnetism. And this is equal to... Well, I need to write that down somewhere, right? It's equal to mu total over V. And V is equal to V0 plus mu 0 M. I'm not writing all that down. M equals CB over T. Curie's law. The quantity C is a constant, different from different materials. I'm not writing all that down. Ferromagnetism, weak field, stronger field. Magnetism follows this goofy little curve or something. I don't know. Thank you. How much time do we have now? Like 30 minutes? 20 minutes? Fuck. Dude, fuck is right. We gotta speedrun all this in 30 minutes. We have to like learn all of this. It took me an hour just to learn the first part, and there are 4 parts, so 3 hours left theoretically. And I gotta do 3 hours and 30 minutes. 3 hours at my highest speed as well, may I just say. Also, this could have probably taught me everything in this entire unit. So low key, new strat. Just read the PowerPoint slides. I'm sorry. This is probably better. Okay, I just read everything. How Faraday's law relates the induced EMF in a loop to the charge and magnetic flux of the loop. How to determine the direction of an induced EMF. How a changing magnetic flux generates a circulating... Can you shut up? How to determine the direction of an induced EMF. How a changing magnetic flux generates a circulating electric field. The 4 fundamental equations that completely... Okay, now don't tease me. The card reader at a gas station scans the information that is encoded in a magnetic pattern on the back of a card. Cool. Why must you remove this card quickly rather than hold it motionless? Huh. Energy conversion makes use of electromagnetic induction. Faraday's law and Lenz's law tell us about induced currents. Maxwell's equation describes the behavior of electric in any situation. During the 1830s, several pioneering experiments with magnetically induced EMFs were carried out, and the future shown a coil of wires connected to a galvanometer. When the nearby magnet is stationary, the meter shows no current, but when I move it up and down, we have the thing called induced current. In this figure, we replace the magnet with a second coil connected to a battery. When we move the second coil toward or away from the first, there is current in the first coil, but only while the coil is moving relative to the other one. Using the 2 coil setup of the previous slide, we keep both coils stationary and vary the current in the second coil by opening and closing a switch. This induced current in the first coil is present only while the second current in the second coil is changing. Okay, a coil in a magnetic field. I feel so smart right now, chat. Shown as a coil in a magnetic field, where the magnetic field is a constant at the shape, location, and orientation of the coil do not change. No current is induced in the coil. A current is induced when any of these factors change. Which factors again? Location, shape, orientation. That makes sense. To define the magnetic flux, we can divide any surface into elements called dA. Magnetic flux through the area element is defined by this guy. Magnetic flux through a flat area. Uh-huh. Between B and A is equal to this. If B and A are in different directions, then we have this guy here. Okay, I assume we're about to get an equation for it. So this guy is the induced EMF. Faraday is equal to D Goofy Lockin' Boy, which is the negative, equals the negative of the time of rate change of the magnetic flux of a... But what is that? The unit of magnetic flux is the Weber, measured in Webers. Determining the direction of an induced EMF. If the flux is positive, becoming more positive. What the frick? Yeah. What am I supposed to do with that? This is an insane diagram. Okay, I got it. Conduction current through path IC plus. This is going to be called the conduction current through path. That's going to be equal to the current. Mesmer from Elden Ring? I don't have time to even make jokes, guys. Chat. Superconductive legion of water. Easy peasy, lemon squeezy. Next question, please. Inductance. Here we go. What the fuck is inductance? Mutual inductance. If the current of coil 1 changes, this induces an EMF in coil 2, and vice versa. The proportionality constant for this pair of coils is a mutual conductance M, which is equal to the guys multiplied by each other. The turns in coil 1 times the magnetic flux through each turn over I2, the current in coil 2. Mutual inductance M. Yeah. B is equal to B0 plus B and M1, this guy M, which we did already. Maybe there's a different way of writing this, and I'm just the smartest man alive. Self-inductance is equal to the number of turns in a coil times the flux due to the current through each turn of coil over the current in the coil. Yeah, I know that. That's easy peasy, lemon squeezy, baby. Alright, so this looks important though. Mutual inductance M. M is equal to N N2 IB2 over I1, which is equal to N1 IB1 I2. Towards the moment current in the coil, and then that's measured in H equal to WB over A, which is equal to 1 joule per A squared. What is a WB, by the way? WB. My wife's a WB, if you know what I mean. Bing bong. 1V over. That's good to know. 1V equals WB per second. That's good to know. It's like an anti-differential to voltage. I don't even want to know what that means. Alright, this is important to read. Potential across a resistor. The potential difference across a resistor depends on the current. When you have a resistor with current I flowing from B to B to A to B, then you find this. A plus minus B. Check. Easy peasy. The potential difference across an inductor depends on the rate of change of the current. When you have an inductor with constant current I flowing from A to B, there is no potential difference. However, if you have an increasing I, so if the inductance is increasing, and that means this little guy right here is going to the left, which is the EMF. So this induced EMF flowing from A to B. Okay. The potential drops from A to B. So this means VAB, the voltage, is equal to L times this, which is greater than 0. So the voltage is positive in this one. And this one, the voltage is negative, basically. Yeah. When you have an inductor increasing the current, then the potential drops. If you have an inductor with decreasing current, which means this, so the I is decreasing. So decreasing current means the potential increases, which doesn't make sense. Think about it more though. Think about it. So when you have an inductor with decreased current's like, if I got a thing and it's going, then that means the potential between the two is going to go up, which makes sense. Magnetic field energy. Energy stored in an inductor is called U. This looks important as well. So the energy stored inductor is equal to L times 0 to 1, and this is the inductance of I di, which is equal to 1 over 2 L I squared. This is final current inductance. Inductance is a different thing, which is L. Okay. The inductance of the inductor makes sense. Magnetic energy density. Magnetic energy density in a vacuum is U, which is equal to the magnetic field magnitude. Okay. Magnetic energy density in material. U is equal to B squared over 2 of these, but this is the mag field magnitude, and this is permeability. The RL circuit. An RL circuit contains a resistor, an inductor, and an EMF force in some way. I've written this down already. The current decay is fucking insane. Suppose there is an initial current I0 running through the resistor and inductor shown. At time t equals 0, we close the switch by bypassing the battery, not shown. The energy stored in the magnetic field of the inductor. The energy stored in the magnetic field of the inductor provides the energy needed to maintain a decaying current. The time constant for the exponential decay of current is equal to L over R. An LC circuit. An LC circuit contains an inductor and a capacitor. Holy moly. This is crazy. It's oscillating. We will show the 4 main steps of this oscillation on the cycle in the next 3 slides. In the LC circuit shown, we charge the capacitor to a potential difference of voltage M, and the initial charge of Qm equals CVm on its left-hand plate, and then we close the switch. The capacitor becomes fully charged whilst the current is 0, and the circuit's energy is all stored in its electric field. Now for the oscillating. The capacitor will discharge through the inductor. As the capacitance discharges, the current increases, but the rate of change of the current decreases. That makes sense. When the capacitor potential becomes 0, the induced EMF becomes 0, and the current has leveled off at its maximum value. Shown is the situation. Although the capacitor was completely discharged, the current persists, and the capacitor begins to charge with polarity opposite to that of the initial state? You could reverse the capacitor. I've heard of this with an inductor. What the hell? Okay, let's look at this energy diagram. So we start with no B, all E. We turn it all into B, then we turn it back all into E, but now the E is the other way. And then we go back to B, and it's the same B that we started with, which doesn't make any sense. But obviously in the reverse direction, later the capacitor is discharged. Why would this be useful? We apply Kirchhoff's rule to the circuit shown. This leads to an equation with the same form as a harmonic studied in chapter 14. The angular frequency of oscillation. Angular frequency of oscillation in LC circuit. This guy is equal to the square root of 1 over LC, which is the capacitance and the other dude. Electrical mechanical oscillations. Okay. Like spring KE becomes ME. I'm a smart guy. I think I remember. PE becomes EE. So you have this 1 over 2 mv squared x plus 1 over 2 kx squared equals 1 over 2 ka squared, which now is 1 over 2 li squared plus q over 2c, which is equal to q squared over 2c. That's good to know. The LRC series circuit. Oh my god. Oh my gosh, chat. We might make it. This is how the practicality of this idea. How phasors make it easy to describe sinusoidal varying quantities. To use reactors. How to use reactants. Okay, we're ending stream here, guys. We made pretty good progress. I will see you guys probably later tonight.